In this lecture, I'm going to demonstrate the use of moment of inertia. When we talk about moment of inertia in an engineering course, it's different than moment of inertia in a physics course. In this case, the moment of inertia I'm referring to is the area moment of inertia. And the area moment of inertia will essentially tell one how easy it is to bend an object. Typically, we symbolize moment of inertia with a capital I, and a larger I means the object is less likely to bend around the axis in question. I'm given this offset beam and asked to find the moment of inertia for that object around the x and y axes. Here's the general form for the area moment of inertia equations for a rectangle. Around the x-axis, the area moment of inertia around the x-axis is 1/12 base times height cubed. Around the y-axis, the area moment of inertia is 1/12 base cubed times height. Whatever dimension is included in the axis, that dimension gets cubed. So when we look at the x-axis passes through the height of the rectangle, so the height gets cubed. On the y-axis passes through the base of the rectangle, so the base gets cubed. Using those notes then, the equation for the moment of inertia around this, using that as a reference, one can see that the equation for the moment of inertia around the x-axis for shape 3 is this. 1/12 a plus b is the base, e is the height, and the height gets cubed because we're dealing with the x-axis. Now I can plug the numbers in, and we'll find that the moment of inertia around the x-axis with respect to that shape is 0.0500 times 10 to the 9th millimeters to the 4th. The area moment of inertia will always have units of length raised to the 4th power. The equation for the area moment of inertia around the y-axis is this. Now we can plug the numbers in. Notice that there is no sign, no direction included on the area moment of inertia. The area moment of inertia only tells us how difficult it would be to bend that shape around a certain axis. It does not indicate direction. Now I'm going to calculate the moment of inertia on the x and y axes for shapes 1 and 2. I already showed you that the moment of inertia of the shape can be found using these equations. However, in the case of shape 2 and shape 1, their centers are not located on the x and y axes. It's not on the origin. There's a certain distance, a non-zero distance to the center of that shape. Because of that, we have to modify the equation. So if we're going to use this as an example, and we want to find the moment of inertia of this rectangle with respect to the chi-axis, here's how we do that. We would take the moment of inertia with respect to the x-axis and add to that the area of the shape times the perpendicular distance to that axis squared. So in this case, this formula would turn out to be this. So this first term is 1/12 b times h cubed. That's the moment of inertia with respect to the x-axis. If we want to find it with respect to the chi-axis, we add to that the area, which is b times h, times the perpendicular distance, which in this case from the center to the axis in question, which in this case is c. The moment of inertia for shape 1 would be ix1, and that equals 1/12. The area for shape 1 is f, which is the width, times the height. The height is j minus e. And since we're looking around the x-axis for the shape, if it was in the center, would pass right through the center. So that goes through the height, which means the height is going to get cubed. Since it's not located on the actual axis, we have to add the area. The area would be f times j minus e, and then multiply that by the perpendicular distance to the x-axis, which in this case is c, and that gets squared. Now we can plug the numbers in. We will find that the moment of inertia around the x-axis for shape 1 is 1.425 times 10 to the 9th millimeters to the 4th. Remember that that's the moment of inertia with respect to the actual x-axis because we added on this second term. The moment of inertia around the y-axis for shape 1 is once again 1/12 times the base times the height. And in this case, the base gets cubed. Now, since this shape is not centered on the y-axis, we have to add that area times the perpendicular distance. The area is F times J minus E, and the perpendicular distance is H. Now we can plug the numbers in, and we'll find that the moment of inertia around the y-axis for shape 1 is 1.9 times 10 to the 9th millimeters to the 4th. I'm not actually going to write down any equations for shape 2. Shape 2 has the same area, and it is located the same distance from the y-axis as shape 1 and the same distance from the x-axis as shape 1. Because the moment of inertia equation doesn't take into account direction or sign, if two shapes have the same area and the same distance from the axis in question, their moment of inertia will be the same. So Ix1 is going to be the same as Ix2. Iy1 will also be the same as Iy2. The last step is to calculate the total moment of inertia on the x-axis and the y-axis. In order to do this, we simply add up all of the moment of inertias we've calculated. Notice that I'm multiplying Ix1 by 2 because there are two shapes that are exactly the same with the same distance to the x-axis. Now we plug the numbers in, and we'll find the moment of inertia around the x-axis is 2.9 times 10 to the 9th millimeters to the 4th. The moment of inertia around the y-axis is the same. We add up all the pieces. We multiply Iy1 by 2 because there are two shapes that have the same Iy, shape 1 and shape 2. Now we can plug the numbers in, and we'll find that Iy equals 5.6 times 10 to the 9th millimeters to the 4th. So at the end of the problem, we put the two values in the box, and we're finished. Once again, the larger value means that the beam would be more challenging to bend around that axis.